So it is with my great pleasure that I introduce Chi Hoi Yip. He'll be talking about conference graphs of non-Paley type. Take it away.
Okay. Okay, so thanks for the introduction and thanks for the organizer to organize this great online conference. So I will talk about conference graph of non-Paley type, and this is joint work with Shamil Asghari, and the talk is based on our preprint, which has been posted on arXiv. So this preprint has around 35 pages, and today I'm just going to talk about a small but interesting portion of our work. So I would like to begin with some basic terminologies before we can talk about conference graph of non-Paley type. So we all know that a graph is regular if every vertex have the same degree. So strongly regular graph is a stronger notion of regular graph. So first, we consider graph X. It has to be k-regular, and suppose it has n vertices, such that any two adjacent vertices have lambda common neighbors. So here lambda is a constant. And also for any non-adjacent vertices, they have exactly mu common neighbors. And we say X is a strongly regular graph with these parameters nk lambda mu. Strongly regular graph have been one of the core topics of interest in algebraic graph theory. And one reason is that we have to use many tools from different branches of mathematics to study strongly regular graphs. Typically, we need to use some kind of algebra, some kind of combinatorics, and some kind of geometry to study them. And here is a list of related subjects. So today, I will mention some connection with group theory, graph theory, and number theory, and also some design theory. Okay. So perhaps it's hard to check whether a graph is strongly regular because we have to check that for any two adjacent vertices, they have the same number of common neighbors, and also for any any pair of non-adjacent vertices. So one efficient way to do that is to use the adjacency matrix and compute the angle values of the adjacency matrix. So if we have a strongly regular graph with this kind of parameters, we can consider its adjacency matrix A and consider the square of A. So we know that A squared ij counts the number of pairs of length 2 from I to j. So for those diagonal entries, we just get the degree, which is k. So we just get the degree of the vertex I, which is k, because x is k regular. And if I is not equal to j and j are adjacent, then each pass of length 2 from I to j is like I and j, and then the middle vertex is a common neighbor between I and j. So A squared ij will be equal to lambda. And similarly, if I and j are not adjacent, then A squared ij would be equal to mu. So based on this observation, we can try to write A squared as a linear combination of A, the identity matrix, and the O1 matrix. And based on this, it's not hard to see that A could have only a few distinct angle values. And indeed, A would have exactly 3 distinct angle values. And one of them is given by K, which is the degree of each vertex. So to check a graph is strongly regular, we just need to compute the angle values of the adjacency matrix, which is sometimes easier. Okay, and in this talk, we will talk about isomorphism problem of a conference graph. So just to recall that we say two graphs are isomorphic if we can find a bijective function between the vertex set of x and y, such that it preserves the adjacency between x and y. And a conference graph is just a special family of conference graph where this kind of 4 parameters are all determined by the number of vertices. So precisely the parameters are given by n minus 1 over 2, n minus 5 over 4, and n minus 1 over 4. And the isomorphism problem of conference graph is that suppose we are given two conference graphs on n vertices, so they have the same parameters as strongly regular graph given by this. And the question we would like to answer is whether they are isomorphic. So usually to show that two graphs are isomorphic is easy because we just need to come up with the right isomorphism. But to show that two graphs are not isomorphic, it's quite tricky because we need to come up with the right notion of invariance. So for example, clique number, chromatic number, or something like that. Or for example, automorphism groups. Okay, and if a family of conference graph is given by the family of Paley graph, and this is an example of Paley graph of order 13. So to construct a Paley graph, first we need to find a finite field FQ. Then the vertices of this graph is just those elements of the field. And the two vertices are adjacent if their difference is a square in that field. So for example, this is the Paley graph of order 13. So the element so the vertices are the element of the field with 13 elements. And we can see that 1 is adjacent to 2 because their difference, which is 1, is a square. But 1 is not adjacent to 3 because we can check that 2 is not a projective residue modulo 13. And in fact, Paley graph is a special Cayley graph. So recall that we would like to construct some new family of strongly regular graph or conference graph. So one way to do that is we can consider certain kind of algebraic construction because we know that a graph being strongly regular is very restrictive. So this kind of algebraic construction would be very helpful. And in particular, we will consider a Cayley graph. So given a abelian group G and the connection set S, so S is a subset of G, which does not include 0, such that S is symmetric in the sense that S is equal to minus S. Then the Cayley graph, Cayley GS, is a graph whose vertices are element of G and two vertices are adjacent if and only if their difference is in the connection set S. And here we require that S is equal to minus S because we want our graph to be an undirected graph. So the Paley graph I mentioned in the previous slide is just a special Cayley graph. So the group G would be equal to the additive group of the finite field FQ, and the connection set would be equal to the set of squares in that field. And it's well known that Paley graph is strongly regular, and we can also compute its parameters, and we can see that it's a conference graph because all parameters are determined by the first entry. Okay, so we know that Paley graph form an infinite family of conference graph. And the interesting question is whether there are other type of conference graph. So namely, we would like to find conference graph which are not isomorphic to any Paley graphs. And we will focus on pseudo Paley graph of non-Paley type. So by a pseudo Paley graph, I just mean a graph which shares the spatial of with a Paley graph. So in particular, it's a conference graph. But at the same time, I would like to make sure that this graph is not isomorphic to Paley graph. So in other words, we consider pseudo Paley graph of non-Paley type. So this kind of graph share many properties with Paley graph because this is already a pseudo Paley graph. That we would like to also find some different properties which distinct this graph with Paley graph, so that we can come up with new constructions of conference graphs. Okay, so I would like to mention about a systematic way to construct strongly irregular graphs. We need to fix a finite field FQ and also fix the choice of primitive root G of FQ. Then this is the definition of cyclotomic causes. So we first fix a divisor n of q minus 1, and we let C0 to be the unique subgroup of FQ star with index n. So FQ star is the multiplicative group of FQ. And we let this C1 up to Cn minus 1 be all the coset of C0. And because G is a primitive root, we can also write Cj as G to the power J times C0. Then this kind of coset are also called the nth cyclotomic causes of FQ. Moreover, we say that these cyclotomic causes are semi-primitive if minus 1 is the power of P modulo n. One important result is given by Brower, Wilson, and Shang in 1999. So their result is that if we construct a Kelly graph defined on the additive group of FQ with the connection set being the union of semi-primitive cyclotomic causes, then the resulting graph is strongly regular. And they can also compute the angle values of this strongly regular graph. So the construction is that we first fix a finite field FQ. We also fix this n. Then we have this kind of n cyclotomic causes. And we pick a subset of them and then take the union of them to form the connection set. Then this KD graph will be strongly regular. And the reason we need to assume that we have this kind of congruence condition is that once this kind of cyclotomic causes are semi-primitive, then there's an easy way to compute the angle values. So if this kind of cyclotomic causes are not semi-primitive, then we don't know whether the construction will give an interesting graph because we don't know how to compute the angle values of the adjacency images. Okay. And next, we would like to use this to give a systematic approach to construct conference graph or pseudo-Paley graphs. So the construction is very similar. We first fix an integer d such a 2d device q minus 1, and we let I to be a d subset of 0, 1 up to 2d minus 1. Then because we are given d, then we can talk about 2d cyclotomic causes C0 up to C2d minus 1. And we can consider the Kelly graph defined over FQ with the connection set being the union of those cyclotomic causes with the index we pick from I. And we denote this graph to be PPQ to the I. And we want our graph to be a conference graph, so we need to assume that this kind of cyclotomic causes are semi-primitive. In other words, minus 1 is the power of P modulo 2D. And because minus 1 is the power of P, then we can write, we can pick the smallest t such that P to T is congruent to minus 1 modulo 2D. And because 2D divides Q minus 1, then Q has to be of this form, P to the 2RT, where R is an integer. Based on the previous result, we can actually show that this kind of construction PPQ to the I gives a pseudo-Paley graph. So in particular, it's a conference graph. And by the way, here we use the notation PP because we want this to be a pseudo-Paley graph. Okay, this kind of construction is very helpful in the sense that it would give rise to a few known families of conference graph. So first, if we consider PPQ to 0, so basically the connection set is a set of squares, and we recover Paley graph. And if we consider PPQ 401, So that's the Kelly graph with the connection set being those element g to the power j, where j is congruent to 0 and 1 modulo 4. So here I will always use g to denote the primitive root. Then we get a Pisa graph, PQ star, first introduced by Pisa 20 years ago. And there's another way to represent the Paley graph, namely we have PPQ2D and we pick those even indices. Then we also get Paley graph. And if we consider the complement of this graph, then we get the complement of the Paley graph. And we know that it's isomorphic to Paley graph itself. And finally, if we consider PPQ to D0, 1, 2 up to D minus 1, then we get the so-called generalized Pisa graph, first introduced by Mullin around 10 years ago. I would like to mention that generalized Pisa graph are natural generalizations of Paley graphs and Pisa graph. Because if we take D to be 1, then we just recover Paley graph. And if we take D to be 2, then we recover Pisa graph. Around 20 years ago, Pisa was able to show that Pisa graph is a new family of a conference graph, in a sense that we can show that if Q is not equal to this for special number, then PQ star is not isomorphic to PQ. And the way he showed this is to, he showed that the automorphism group of PQ star is strictly less than the automorphism group of PQ. Based on this, I guess Mullin conjectured that generalized Pisa graph are also a new family of conference graph. So basically, we confirm this conjecture. So we show that if these at least 3, then this kind of generalized Pisa graph are not isomorphic to Paley graph and Pisa graphs, up to some small exceptions. So we need to assume that Q is sufficiently large, or Q is not equal to a few special values. Okay, and instead of proving this, I just want to quickly sketch a proof of this, a special case of this result. So we consider X to be PPQ to the I. So this is the semi-print which show the Paley graph, where Q is equal to P to the 2RT and I is even. Then we show that X is isomorphic to the Paley graph if and only if I is given by the set of even numbers or the set of odd numbers. So we know that in these two cases, X is trivially isomorphic to the Paley graph. And the way we show this is proof by contradiction. So suppose that I is not equal to these two sets and X is isomorphic to PQ. Then we know that the number of maximum clicks in these two graphs has to be the same, And we know how to classify maximum clicks in PQ. So indeed, Brockhaus showed that the only maximum clicks in PQ contain 0, 1 is given by the subfield with square root Q element. So here Q is a square, so it makes sense to talk about the field with square root Q element. And because X is a Kelly graph and X is isomorphic to PQ, it's easy to see that X also has a unique maximum click containing 0 and 1. And note that here, typically we'll imagine that the number of maximum click of a graph will be like huge because we have a lot of automorphisms. But here we have a unique maximum click because it's easy to see that this kind of subfield is fixed by many, many automorphisms of the Paley graph PQ. So because we know that X also has a unique maximum click containing 0 and 1, so this unique maximum click also has to be fixed by many, many automorphisms. So that means this unique maximum click must be very, very special. So let's try to guess what would be the reasonable choice of this maximum click. So to do that, we first need to recall the definition of our graph. So recall that we have a Kelly graph with the connection set being the union of those cyclotomic classes with index given by I, with index given in I. So so we can see that our graph is actually a union of many copies of the same graph. So it makes sense to talk about the contribution of each cyclotomic causes forming the connection set to this maximum clique. So because we have this subfield FUQ, it's easy to write down this in terms of the contribution of each cyclotomic causes. So this is given by zero union, this kind of union, where A0 is a subgroup with index D times through Q plus 1, and G is the primitive root of FQ. And you can see that FQ minus 0 is basically a union of coset of A0. And the precise coset are those G to the power 2J. So you can see that this kind of 2J appears in the index set, because the index set for a Paley graph is just those even integers. So this would motivate us to come up with a natural choice of clique in PPQ to the I. So we just need to replace this kind of index 2J by the corresponding index like MJ. So this will be a reasonable choice, a reasonable guess of the unique maximum clique containing 0 and 1 PPQ to the I. And in fact, we can show that if C is a maximum clique containing 0 and 1, then we can always find another maximum clique containing 0 and 1 where some kind of automorphism of X, unless C is given by this clique. So that means this kind of naive guess will be the only candidate of the unique maximum clique. And finally, we just need to rule out this choice. Okay, because we already know what's the candidate, then we just need to show that this is not a clique. So that's not too difficult. So based on this, we are able to show that we give rise to a new family of conference graph of non-Paley type. So that concludes my talk. Thank you very much for attention.
Let's give a round of applause for Chi Hoi Yip for a great talk. Okay, I'll open up the floor now for any questions anyone has. If you want to unmute, you can do that, or you can ask questions in the chat, or just raise your hand, or whatever you want to do.
Am I correct in my understanding that a strongly regular graph's complement is always strongly regular, but a conference graph's complement is basically you need n to be a very specific number for that to work?
So I guess, yeah, I guess the complement of a strongly regular graph is always strongly regular, and maybe that's also true for a conference graph.
It feels like because you've got like -5 and -4, like in
all right, yeah.
In some way those parameters are going to flip themselves, I think. And so, yeah, I don't. It's not something you know off the top of your head. It's something I could probably do with arithmetic if I tried.
Yeah. Yeah.
Okay.
For example, we know that so in our construction, all these graphs are actually self-complementary. So they are isomorphic to the complement, because the complement of this is just like we pick a complement of the index set.
Mm-hmm.
Yeah, so actually we construct like self-complementary conference graphs.
Okay.
Okay, any more questions? So I have one more question. I was looking, have you tried looking at sort of different constructions involving different type, like different types of algebraic objects, like looking at FQ to the N, or looking at like GLN FQ, different types like that way, and then trying to figure out like what should a cyclotomic class be in those settings?
So I haven't, but I know some different construction of conference graph based on finite geometry.
Okay.
So, I mean, this kind of construction is a particularly nice construction, but there are other kind of construction which may not come from finite field. So there are also conference graph with order which is not necessarily a prime power.
Right.
So the short answer is I haven't tried that, but I'm sure there are some related constructions.
Okay, cool. Thank you. Okay, any other speakers? Or sorry, any other questions for the speaker? If not, let's give him another a round of applause.